Hello Geometry, this is the chapter 12 video on arcs, chords, and angles. So we're going to get right into it, not waste any time, and do the circle stuff that we need to do. Alright, so first of all, central angle and an arc. What is a central angle and what is an arc? A central angle is an angle whose vertex is always right here at the center. I'm going to put angle 1. So I'm going to put central angle, and that is angle number 1. And the arc is the arc that central angle hits. And I'll put like AB here. AB is the arc. So the arc will be AB. And what you do is you put a little arc. We used to have a segment, if we want to say a segment, a line with arrows if we wanted a line, or we have a ray. We put a dot and we put an arrow. Well, that's a notation for the arc. And there's a really big theorem that goes along with this. And the theorem is whatever the central angle measure is exactly whatever the arc measure is. So these two things are equal. Angle 1 is equal to the measure of the arc. And sometimes they'll put a little m here. Stands for the measure of arc AB. Sometimes you'll see that, sometimes you won't. But both are measured in degrees. So let's say this is about, I don't know, maybe that's 88 degrees. Well, then this arc AB here would be 88 degrees. If you went all the way around the circle, you'd have 360 degrees. Half the circle, you'd have 180 degrees. There's a lot of math going on here, but that's the first part. The arc and the central angle are equal. There's three types of arcs. There's a major arc, a minor arc, and a semicircle. So I'm going to I'll call this circle P. I'm going to call that A. I'm going to call that B. I'm going to call that about C right there, and then I'll call this point D. A, B, C, D around the circle. So first of all, a major arc is between 180 to 360 degrees. 180 to 360. So more than half the circle is a major arc. So if I wanted a major arc, it takes 3 letters to name it. So let's say I wanted this major arc right here. I could call it ABD. I could call it ACD. But I want to say start here, go in that direction, and go back around to D. Okay, so like ABD. Let's call it a major arc. Major arc would be like major arc ABD between 180 and 360. A minor arc is 0 to 180 degrees. 0 to 180 degrees, so less than half the circle. Whole lot of minor arcs here. One minor arc, another minor arc, possibly a minor arc from B all the way around to D. Another minor arc, another minor arc. I'm just going to say, let's say A to B is a minor arc. Okay, whatever that arc A to B here. And it only takes 2 letters to name a minor arc. So right away you can tell just by the notation if it's a minor arc or not, if it's 2 letters or 3 letters. And then the last one is a semicircle. It's equal to 180 degrees exactly. And we would know that this is a diameter here. That diameter would divide the circle in half. And we could say A, B, C is a semicircle, or we could also say ADC is a semicircle, and you use 3 letters to name a semicircle also. That's the common notation of what arcs look like. There is a arc addition postulate, a rule that says, hey, if you add arcs up, you'll get the whole arc. So maybe I have A, maybe I have a B here, and maybe I have a C here, and I'll put my center here, okay? And it looks like from A to C is a major arc. So I'm going to say the measure of arc ABC, that arc, should be equal to the measure of arc AB plus the measure of arc BC. And again, sometimes you'll see the M's in there and sometimes you won't. Sometimes I'll drop them out just because I don't like writing them in all the time, but that's the way that it looks. Maybe it just says ABC equals AB plus BC, But we had another name for this. We just said this part plus this part equals the whole thing. And our rule here was small part plus small part is equal to the whole part. And that really applies with arcs too. If you take the two little small baby angles, you'll get the whole big angle. Alrighty? Some rules now with chords, arcs, and central angles. Number one, if you have congruent chords, you have congruent arcs, and then you have congruent central angles. So the first one says, and all three of these are basically, all three pictures are going to say the same thing in a different order. The first one says, if these two blue chunks are congruent, if that's the same as that, if the chords are congruent, then we're going to have arc AB and arc CD are going to be congruent. So I'm going to put in this, if we have the blue part, then A to B, the arc, is going to equal D to C, the arc. So I can put a little tick mark there and a little tick mark there. And more than that, the central angles will also be congruent. So I'll draw in these angles here and that angle there, and I'll put a 1 and a 2 in. If the blue parts are congruent, then the arcs are congruent, and angle 1 is the same as angle 2. Congruent chords yield congruent arcs and congruent central angles. Congruent arcs. If the blue part. So now I'm going to say that this arc here, let's call that arc XY, is the same as this arc over here. I'm going to make them about the same, WZ. So we're going to start with the fact that that is the same as that. Well, if the blue part, then the red part. Then that will be the same as that, and the central angle will also be the same as that. So if the blue part happens, we can then also say segment XY is the same as segment WZ, and we can say angle 3 is the same as angle 4. Angle 3 is the same as angle 4. And I'm going kind of fast to shorten up this video. Feel free to press pause as you need to copy down the picture. So if the blue part, then the angles are the same and the chords are the same. And then the last thing here, same type of deal. This one says if the angles are the same, maybe angle 5 is the same as angle 6. I'm going to put little congruencies in there. If 5 and 6 are the same, then this following red part will happen. Then, hey, I'll put KL and MN. If the blue angles are the same, then K to L is the same as segment M to N. Then KL, the segment, is congruent to KL, the segment, MM, the segment. And the other one would be KL, the arc, would be the same as MN, the arc. KL, the arc, would be the same as MN, the arc. So those would be the same. And basically, all three of these little pictures, they're saying the same thing. If you have congruent chords, you're going to have congruent central angles, and you're going to have congruent arcs. They all go together. They're intertwined. Okay? Last one. A diameter perpendicular to a radius bisects both the arc and the chord. And I'm going to freehand this. Okay, a diameter or a radius. I'm going to draw it in as a diameter. So I'm going to go like this. That's perpendicular to a chord. Bisects both the arc and the chord. And the best way I can tell you about this is if you have some type of diameter or radius and you have a right angle, it's going to form a cross or a kite. And all of those rules that applied were congruent. If this happens, you can come up with all of these blue things. And I'm just simply going to mark them on the picture. This little arc would be the same as this little arc. this chord would be the same as this chord. This arc from here to here would be the same as this arc from here to here. If you were to draw a segment in and a segment in, like the top of the kite, those segments would be the same. I'm going to draw little circles in there. Same way down here, if you drew those segments in, I'm going to put 2 circles on that one, and here I'll put 2 circles on that one. I mean, if this happens, if this red part happens, there's just a whole lot of congruencies that pop up. The part that they talk about the most in this section is that chord gets cut in half and that arc gets cut in half also, which means then those 2 pieces right there would also be congruent. Okay, let's look at a few examples of this. I'm going to blow this up. Oh, let's go to 200% here. Let's view a bigger view. There we go. An arc that joins the endpoints of a diameter is called. All right, let's do some of these. An arc, oops, let's make it smaller. An arc that joins the endpoints of a diameter. So here's a diameter, and they're talking about the arc that joins those endpoints is called from there to there. Well, that's a semicircle. How do you recognize a central angle of a circle? Pretty easy. I'm going to draw a picture. A central angle, the vertex is at the center. Central angle, vertex is centered. In circle P, ABC, the arc ABC is 205 degrees, therefore ABC is a major arc. It's a big arc. In a circle, an arc that is less than a semicircle is an arc less than a circle is a minor arc. And we got it. Just some vocab over what we just went through. All right. Consumer application. Use the following information, exercises 5 through 10. The graph shows how typical household spends money on energy. Find each of the following. So you can tell in your household, heating and cooling are probably the biggest thing that happens in your house. There's a lot of energy that goes into that. Your water heater takes up a lot. Fridge, dishwasher, washer, and dryer. Your dryer especially takes up a ton of things. And then lighting, and then your other would be your devices and stuff like that. So they want angle PAQ. Angle P to A to Q. Okay? And they're telling me it's 45% of the circle. This is an extremely common ACT problem. I have seen this ACT problem over and over again. They give you a percent of the circle and they want to know what the degree measure is. Well, I have 45% of a circle. That's 45%. 45% of 360. And if you want to do that, you take 0.45 times 360. You change your percent to a decimal, and then you multiply. Looking for my calculator here. I'm going to do that right now. I'm going to take 45% of 360. 0.45 times 360, and I got 162 degrees. And that makes sense. It looks like it's a little bit under 180, so I'm in good shape there. They want to find the angles now. BAU. I don't even think we need to do this. We would take 7% times 360. SAQ, angle S to A to Q. Oh, that one and that one. I would have 6% and 11%, which would be 17%. So I would multiply by 0.17 times 360. They want UT and RQ. They want U to T, that arc. U to T is 10% of 360. And remember, the angle in here is the same as the arc out there. So if I take 10% of 360, it'd be 0.10 times 360. I can do that in my head. That's 36 degrees. And R to Q. R to Q right here. Well, R to Q would be the same as the angle inside of there, but it'd be 11% of 360. So I can do 11% of 360. Last one, UPT. U to P to T. U to P to T. Oh my goodness. I'm going to erase that. U to P to T asks me to start here, go around to P, and all the way over to T. Well, it would be everything except for 10%. So it would be 90% of 360. I would take 90% of 360. I'm going to go ahead and do that one on 0.9 times 360. And I got 324 degrees. All right, let's keep going. A couple more example problems. Okay, it wants me to find each measure now. So this one is D to F. It wants to know the exact degree measure of D to F. Now, which way would I go if it has two letters? That's a common mistake. Well, the two-letter problems, if it has two letters, it means go the short way. So let's fill in some measurements here. That's 51, that's 90. Well, this little, see how it's a straight line right there. So 90 plus 51, if I subtract those two from 180, I'm going to go 90 plus 51, I get 141 subtracted from 180. I know this right here has to be 39 degrees, and then this over here would be 39 degrees. And then I could find this slice right here because I have a straight line, and that's already 39, so this would be 141 degrees. So my first step would probably be to write all that stuff in if I was doing a problem like this. Now I want D to F. D to F, well, that's 90 plus 39. And that's 129 degrees. DEB. D to E to B. D to E to B. So that DEB would be 90 there, and then I have 180 more degrees, so that's 270 degrees. J to L, the arc. J to L, here to there. Well, J to L, well, I have 30 there, and I have, again, I have a straight, here's a half of a circle. I know there's 180 degrees in that half a circle. So I'm going to take 180, and I'm going to subtract off what's already there. I'm going to subtract 30 and 72 from 180, and that means this angle right here is 78 degrees. So J to L would be 78 plus 30, which is 108 degrees. HLK, start at H, go to L. Well, H to L is 180, and then that much more to K. 180 plus 30, it looks like, is 210 degrees. 210 degrees. Okay, a couple more. Angle PR, angle QPR, Q to P to R, so that angle, oh, they already marked it, is equal to RPS, that one. It wants us to find the length of Q to R, and it didn't say it, but it'd be Q to R, the segment length. Now, two angles are the same, and the rule was if the angles are the same, the arcs are the same, and the chords are the same. So if these two angles are the same, these two chords are the same. And I can set 8y minus 8 equal to 6y, and I can solve it out. I'll minus the 8y. I get negative 8 equals negative 2y when I subtract those two, and I got a y value of 4. It's not the answer. The y value is 4. It wants us to find the length of Q to R. So I take the 4 and I plug it in. 8 times 4 is 32. 32 minus 8 is 24. Q to R is 24. Next one. In circle A and circle B, the C to D, this arc is the same as this arc. Well, again, if the arcs are the same, the angles are the same. So these two angles right here would have to be the same. 45 minus 6x should equal negative 9x. Okay, that should work. I will add 6x over. I get 45 equals negative 9x, and 6x is minus 3x. And that means my x value, 45 divided by negative 3 is negative 15. It wants us to find angle EBF, this angle right in here. Well, I take that and I'm going to plug it in for the x. I'm going to take negative 15 times negative 9. The negatives will cancel out, so basically I'm doing 15 times 9, and that angle right there is 135 degrees. So when you get problems like this where it shows you congruent arcs or congruent angles or congruent chords, what you're going to do is you're going to probably see what's congruent and then set the two chunks equal to each other. Maybe plug something back in after that. Last two problems, multi-step. Find the length of the nearest tenth. It wants r to s. R to s to the nearest tenth. I have a 5 and I have an 8. Well, let me see here. That distance. I have a radius drawn in. Well, this radius is 8 plus 5. So this radius right here would be 8 plus 5, or 13. Okay, I wonder what I'm going to use in this picture here to find that x value. Yep, it's another Pythagorean theorem problem. 5 squared plus x squared equals 13 squared. 25 plus x squared equals 169. X squared equals 169 minus 25 is 144. My x value is 12. Okay? It wants r to s. The rule was if I have a radius or a diameter that's perpendicular to a chord, it cuts the chord into two equal halves. So if that's 12, and that's 24. Okay, 24 right there. Let's try it again. Let's try another one like it. So I got a little chunk that's 20. I got a big chunk that's 50. That means this radius right there, it wants E to F, that distance across. That radius right there would be 50 plus 20, which is 70. And I can use the Pythagorean theorem to find that little chunk right there again. So I'm going to do 50 squared plus x squared equals 70 squared. These are big calculators. I'm going to do 70 squared minus 50 squared on my calculator just to see what I get. Because what I end up doing is I end up subtracting the 50 squared over whatever that is. So I get x squared is equal to 70 squared minus 50 squared is 2400. And let's see if that's even. And I got 48.99. 48.99. And I'm going to leave it like that. And then if I wanted the distance from E to F, I would multiply that by 2. And I got 97.98. E to F, 97.98. All right, that was the first part of the notes for this chapter about arcs, chords, and inscribed angles. Hopefully you took great notes. Go back if you need to and look at some of the examples. And good luck.